Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the graph of cubics. So firstly, we're going to look at transformations of cubics. This here is the graph y equals x cubed. So this point for y equals x cubed at the origin is called an inflection point. So I guess it's kind of analogous to the turning point of a parabola. It sort of divides the graph into two pieces. See, here it's like concave down, and here it's like concave up. Here it's like a frowny face, and here it's like a smiley face. So this inflection point changes concavity. It changes it from being a frowny face to a smiley face, or vice versa. So that's important because we're going to track the location of this inflection point when we apply transformations. Now, when you apply transformations to cubics, the same thing happens as when we applied them to quadratics or hyperbola, or indeed any function. So if you take a function and you replace x with x plus b, it translates left if b is positive or right if b is negative. Remember, this left or right goes sort of the opposite way than we would expect. If you add a constant at the end of a function, it translates it up if it's positive, down if it's negative, and if you change the sign of the whole thing, if you stick a negative out the front of a function, it reflects about the x-axis. So what does this mean? Well, let's say I want to graph this one here. So y equals -2 outside of x minus 1 cubed plus 4. So from what we know here, this one here has translated it up 4 units. This one here has gone 1 unit to the right. Remember, it sort of goes the opposite way we'd expect. And because this number out here is negative, that means it's going to be reflected. So the inflection point of a cubic is normally here at 0, 0. But because this has been translated 1 unit right and 4 units up, the inflection point of our graph here will be here. So the inflection point is 1, 4. Okay. Now, what we want to do is find the y-intercept, because that's not actually hard. Now, to find the y-intercept, all you do is let x equal 0. So I would get y equals -2, 0 minus 1 cubed plus 4. So I get 2, positive 2, plus 4 is 6. The y-intercept here is 6 up here. So other than that, this has just been reflected. So instead of going this way, it's going to go this way. It's been reflected about the x-axis. Other than that, it has the same shape as a cubic. So what's going to happen is it's going to start off here as a smiley face. At the inflection point, it's going to change into a frowny face. So that's what the graph here will look like. So that's how we graph transformations of cubics. Now let's graph them by calculating intercepts. So now we're going to look at graphing cubics whose equation is in this expanded form here. Because if it's in this form, it's not at all obvious what transformations were applied to y equals x cubed. So we need another method. So this method involves us finding the y-intercept, the x-intercepts, the orientation, and then graphing. So let's graph this one here. So the y-intercept is just d, it's just the constant term. So this has a y-intercept of 5, I'll just mark it there. So that part's easy. Now finding the x-intercepts is a lot more work. To find the x-intercepts, you need to let y equals 0, and then you need to find the first root, so you can find a factor, and then once you found a factor, use synthetic or polynomial long division. The goal is we want to factorize this. So I won't go through the whole process of factorizing. I went through that in another video, but if you factorize this, it turns out you get x minus 1 squared times by x plus 5. So the two intercepts here, the two x-intercepts, are 1 and -5. Now, unfortunately, when we're doing cubics, we need to determine which type of root we have. 1 and -5 are the roots, but are they single, double, or triple roots? Now, that's totally determined by the number of times they appear as a factor. So because x minus 1 occurred twice as a factor, because it had the power of 2, 1 is actually a double root, whereas x plus 5, there was only one such factor, it is actually a single root. So whether a root is single, double, or triple depends on the power of its associated factor. So if you had x minus 1 cubed, 1 would be a triple root. X minus 1 squared, 1 would be a double root, and x minus 1 just by itself would be a single root. Single roots cut the x-axis, double roots bounce off the x-axis, and triple roots are inflection points. That's what I mean by this wiggle here. So finally, let's determine the orientation. So because a, the coefficient of x cubed here is 1, so it's positive, it'll be up here and down here. So this is what's going to happen. Over here at -5, there is a double root. Here there is a single root, and it's going to start down here and up here. So it's going to come through and it's going to cut the x-axis at -5. Now at some point here it has to stop and turn around. You don't need to know exactly where the turning points are for cubics because you need calculus to do that. So just estimate. It's going to stop and turn around somewhere. It's going to go through y-intercept of 5. Then it's going to come down to x equals 1. That's a double root, so it's going to bounce off this axis, and then it's going to go on forever in this direction. That is the graph of y equals x cubed plus 3x squared minus 9x plus 5. Now let's just do a quick example where we're given the graph and we find the equation. So we're going to calculate the equation of this cubic here. So we know that it has 3 intercepts at -3, 1, and 2. So that means the equation will be able to be written in the form of something times x minus 3, so x plus 3, times x minus the next intercept, times x minus the next intercept. So we just now need to find a, and we've been doing questions like this all term. You substitute in a point. Let's choose the y-intercept of -2. So I'm going to substitute y for -2 and a for 0. So I get a times 0 plus 3 times 0 minus 1 times 0 minus 2. Of course, 3 times -1 times -2 is positive 6. I've got -2 equals 6a. Divide each side by 6, you get a equals -1/3. Now that makes sense because it was going up here and down here, we knew that a had to be negative. So the final equation we can just leave as y equals a times x plus 3, x minus 1, x minus 2. It'll be a bit of effort to go through and expand this, particularly with a negative fraction out the front, so we'll just leave it like this. If you were to graph this equation here, you would get that graph there. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.